So thank you very much for inviting me to speak at this workshop. And so let me apologize that I cannot attend in person. And thank you for giving me a chance to deliver this talk in online. So today I'm going to talk. So the title is Polynomial Progressions in Topological Fields and Their Applications. But so in fact, there will be the last slide about this. So I will talk more about equidistribution and something that arose during this semester, this year at the institute. And so I would like to tell you some stories. So let me start from classical, from the equidistribution criterion of Weyl, and let me remind the definition of sequences which are equidistributed. So if we consider a sequence in the unit interval, so it's equidistributed if for every continuous function the following limit exists. And so the famous criterion of Weyl says that sequence is equidistributed if and only if the following averages converge to 0 for every non-zero integer. So in other words, we can think that this limit restricted to the Fourier characters it's 0, because if we integrate the Fourier character whenever m is non-zero, then we see that this is 0. So in other words, so it suffices to verify the existence of these limits in a dense class, or some objects that generate, we know that linear combinations generate a dense class in the space of continuous functions. So this is why we can restrict our attention to the limit of this form. And this is very useful in many applications. And the third condition, presumably the most the one that is usually in many textbooks used as a definition of equidistribution, is this one. So it says that the number of visits of the sequence an in the interval, subinterval of the unit interval, is proportional asymptotically to the length of the interval. So that's the Weyl criterion. And so one of the classical results about the equidistribution, which was proved around 1910 of the previous century, it was proved by Weyl and independently by Boch and Sierpiński. So it says that if we have irrational number, then fractional part of n times the irrational number theta is equidistributed in the unit interval. And few years later, so this result now can be easily verified if we use this this condition, the statement from item B of this criterion. So it suffices just to some, because of the irrationality of theta, it suffices to some geometric sequence of characters, and we are done essentially. And but few years later, Weyl showed that if we consider a polynomial having at least one irrational coefficient, then the fractional parts of this polynomial is equidistributed in the unit interval. And so this is a very interesting paper. So I had a chance to look at this paper recently when I prepared this talk. And one of an important consequence of this paper is Weyl inequality for exponential sum, which is very important in number theory. So it says that if we have polynomial, and for instance, if the leading coefficient is approximated by a rational fraction in this way, then this normalized exponential sum can be estimated in this way uniformly in and Q. So I was unable to find explicitly in Weyl's paper this this inequality, but of course, the method that leads to this conclusion, it's very clearly stated in Weyl's paper. And now let me show you, because I started to think about if this can be, that was some time ago, if this can be used to derive, for instance, this result that the fractional parts of P of n are equidistributed in the unit interval using this inequality. And I was unable to do this. I started to browse on the internet, and I found a very nice discussion on Math Overflow about and someone raised this question if it's possible to use this inequality to derive the equidistribution theorem for polynomials. And so the conclusion essentially, so we can take a look on the internet. So the conclusion essentially is that it's not clear. But so let me show you how Weyl methods can be used, for instance, to show that alpha n square is equidistributed modulo 1. This is just for fun, to showing you how to use the device IDS. And so this is what we do if we have sequence, if we have an irrational number, then by the Dirichlet box principle, we can find an infinite sequence of rational fractions an over Qn, which are coprime, and Qn is controlled in this way, so it does not exceed capital N. And so the rationals approximate alpha in this way. And of course, because alpha is irrational, one can easily show that this limit is diverges to infinity. And now if we apply the Weyl differencing, so in other words, we consider the square of this exponential sum, we open the square, we change the summation, and then we reduce the method to a linear polynomial. We use the we sum geometric sequence, and we obtain the following bound. And now we see that this bound, so for n equal 0, so we have minimum of two numbers of this form. So for n equals 0, this quantity that we have here, it's completely useless. So therefore we put n, and for non-zero integers we have this bound. And now it turns out that this because of this approximation here, it can be controlled by the expression of this form. So, and if we multiply, then we end up with the following inequality: n times log n plus n square over Qn. And now if we divide everything by n square, then we see that this converges to 0, and by appealing to a Weyl criterion, we see that this sequence is equidistributed. And this is essentially how Weyl proved his equidistribution result. So that was very instructive, to take a look how it was in Weyl's paper. And so I wanted to share, because I think that this is a very nice argument to see, and especially in the context of n squares, it's very instructive to see how it works. But now, so let me change the topic. Let me tell you something about the result of Khinchin from 1933. So he was able to extend the Weyl equidistribution theorem to the Lebesgue measurable sets. And he observed that if we use Birkhoff-Ergodic theorem, Pointwise Ergodic theorem, which asserts that for every function in LP, whenever P is bigger than 1, bigger or equal 1, then the following limit exists in measure preserving systems. And this limit is understood in the LP sense and almost everywhere. And so, and Khinchin had so he observed that this can be used to extend the equidistribution theorem of Weyl and prove the following results. So here, because we replace now intervals by the Lebesgue measurable set, so by the nature of Lebesgue measure, so we have to ask about pointwise convergence almost everywhere, and we have this result, which is a simple consequence of the Birkhoff ergodic theorem. And and then there was a famous in the early 80s of the previous century, a famous question of Bellow and Furstenberg asked whether the same conclusion holds in Khinchin's results if we replace n with any polynomial with integer coefficients. And so this question was answered in the affirmative by Bourgain in the mid of 80s, late 80s. So he was able to show that whenever p is a function in LP and p is between 1 and infinity, then the following convergence holds almost everywhere. And so therefore this here now we see that this problem, so this theorem gives positive answer to Bellow and Furstenberg, but also it was a trigger to understand the nature of sequences AN for which we have pointwise almost everywhere convergence. And so here too there are two natural definitions. So we say that a sequence AN of natural numbers is LP good if the pointwise convergence for this ergodic averaging operators along AN holds for every dynamical system and for every p in LP. And otherwise we say that AN is LP bad. And now let me illustrate let me give you some examples. And so how the things developed over the years since Bourgain's paper. So of course, if we take AN equal n, then the classical Berkov-Ergodic theorem says that this sequence is LP good for any p bigger or equal 1. And of course, Bourgain theorem implies that Pn, the sequence of for polynomials, we have LP. So this sequence is LP good whenever p is bigger than 1 and p is any polynomial with integer coefficients. And so Bourgain at that time also considered the sequence of prime numbers. That was also part of Bellow question. And so in fact, in 1989, Bourgain and Weyl were able to show that if we consider the ergodic averaging operators over the prime numbers, then the sequence is LP good whenever p is bigger than 1. So, and at that time, the question about the endpoint estimates for p equal 1, it was a major open problem in pointwise ergodic theory, and it led to some remarkable conjecture of Rosenblatt and Weyl from 1991. And so there was so the conjecture says that if we consider a sequence with gaps tending to infinity, so in other words, if these differences diverge to infinity, then okay, sorry, let me put it this way. So the conjecture states that there are no sequences of integers with gaps tending to infinity satisfying this condition, which are L1 good. So in other words, we cannot expect pointwise convergence whenever p is equal 1 for sequences which have gaps, or even it was conjectured that if we consider sequences which have 0 upper Banach density, then they also should be L1 bad. And so, but in the meantime, people studied the LP theory for p bigger than 1, and so there is a beautiful paper of Bozernician, Kolesnik, Kwas, and Wirt from 2005, where there is an extensive discussion about LP good and LP bad sequences. And for instance, as a conclusion, so if we consider functions h of x, which are of this form, so in other words, this is some function which grows polynomially, like x to c to power c, and multiplied by certain function which is slowly varying, then this sequences, an integer part of the functions of this form, they lead to LP good sequences. But so what is interesting, in 2007, Urban and Zienkiewicz, they disproved the Rosenblatt-Wirth conjecture, and they gave a very explicit sequence. Okay, so they gave a very explicit sequence, n equal to integer part of n to power c, and whenever c is between 1 and 1.001, then they showed that we have pointwise almost everywhere convergence for ergodic averaging operators along an, which is of this form. And this gives a negative answer to Rosenblatt and Wirth conjecture. But essentially, at the same time, Buchelich and Moldau, and also not long afterwards, La Victoire, they showed that if we consider kth powers, then this sequence is L1 bad, which means that we don't have pointwise convergence for the sequences of this form. And also, if we consider an, which is the nth prime number, then La Victoire also showed that this sequence is L1 bad. So that's the picture showing what happens in this business after Bourgain's paper. So let me also mention that at some point I was also interested in this kind of problems. Especially, I was inspired by the paper of Urban and Zienkiewicz and started to think about this. And I was able to show that if we consider a sequence of this form, in integer part of h of n, where h of n, this is n to power c times slowly varying function, and c, it's of this form 30/29, which is approximately 1.03, then then this sequence is L1 good. So in particular, I was able to show that there exists a universal constant that for any sigma finite measure preserving system, we have weak type 1,1 inequality for the sequences of this form. So, and this inequality, if we have this inequality, then we can deduce pointwise convergence on L1. Okay, so and this is what I wanted to say about these LP good and LP bad sequences. And now let me pass to the definition of unique ergodicity, which can be thought as a certain concept that allows us to detect sequences which are uniformly distributed, or orbits which are uniformly distributed in continuous dynamical systems. So here is a very nice theorem which says that for a continuous map, suppose that we have a compact metric space and a continuous map which maps X to itself. And so then the following properties are equivalent. So T is uniquely ergodic, so which means that the space of all T invariant measures consists of precisely one measure. And then this is equivalent that for every continuous function, for every X, we have the following convergence, where mu, this is this uniquely ergodic measure. And in fact, this theorem says that this convergence is uniform across X. And also, we can show that this convergence can be only verified for functions from a dense class, dense subset of the space of continuous functions on X. So that's a very useful result, which in particular, it allows us to deduce the fact that if we consider polynomials with at least one irrational coefficient, then this sequence, the fractional parts, it's uniformly distributed in the unit interval. And in particular, so here this convergence says that this sequence, the orbits of X are uniformly distributed in our compact metric space. And now let me tell you about a very nice question of Bergelson from the mid of 1990s, as far as I know. So it says that if we have a if we consider a dynamical system which is totally uniquely ergodic with unique t invariant measure mu, and we consider a polynomial with integer coefficients and continuous function. So the question of Bergelson was, is it true that for all but first category set of points, we have the following convergence? So in other words, here we consider Bourgain's averaging operator along polynomials. Our function is continuous, and we ask about, this time, everywhere convergence except the set of first category in X. And so this problem was open for a few years, and so a counterexample was provided to this question by Ronnie Pavlov, essentially in the year of 2008. And so he was able to prove the following result that shows that for any increasing sequence with upper Banach density 0, there exists a totally minimal, totally uniquely ergodic, and topologically mixing topological dynamical system, and a function, continuous function, with the property that for a residual set of points, the average along AN, along this sequence, having upper Banach density 0, does not converge. So therefore, so in particular, if we consider polynomials, then this then we don't have this convergence. And from this paper, it also follows that this is if we consider the set of prime numbers, AN is a sequence of prime numbers, then we don't have this convergence. But this presumably was not explicitly stated in Pavlov's paper. So I learned about this from Mariusz Mirek. Yeah, so this result shows that so here the situation in the uniquely ergodic systems, in the topological dynamical systems, the convergence may be completely different. We have a completely different nature. We can expect completely different nature of these sequences. And now let me tell you, in order to show you that to completely destroy this is what completely destroyed my intuition about the sequences, was the result of Bergelson and Richter at their beautiful prime number theorem, dynamical prime number theorem. So if we consider a sequence omega n, which is which denotes omega n, so assume that omega n denotes the number of prime factors of a natural number n, which is counted with multiplicities. So the theorem of Bergelson and Richter says that if X is uniquely ergodic topological system, then we have this convergence. So in other words, the averages of this form along omega n converge everywhere. And so in particular, this implies that for every irrational alpha, the sequence alpha times omega n is uniformly distributed modulo 1. And so here, and this is what is very surprising here, is the recent result of Lloyd, which shows that if we consider any non-atomic ergodic probability measure preserving system, then there exists a measurable set for which the ergodic averaging operators evaluated at the characteristic function of this set have a strong sweeping out property. In other words, so the lim inf for the averaging operator of this form is 0, and the lim sup is 1. So therefore, and this holds almost everywhere. And this shows that we don't have pointwise almost everywhere convergence. And the reason, so I have to say that I have been thinking about this, and so the first, the best what I can say at the moment is because this sequence takes every integer infinity often. So in other words, it returns to every integer infinity often. So this is not an increasing sequence. It oscillates. It's a highly oscillating sequence, and I think that this is the reason. But so this is the best what I can say at the moment, and I want I would like to try to understand this problem more carefully. So this is something that I have been thinking about. So for instance, I'm wondering, so what happened, for instance, if instead of omega k, we consider k plus omega k? And I want to understand if this sequence, if for this sequence we have pointwise almost everywhere convergence. So that's something, that I want to understand these days. But I wanted to show you this story because I think that, it's a nice story, to see the differences between these sequences. It's very interesting. And now let me change a little bit and tell you something about a very interesting result of Arkhipov, Zubarikov, and Karatsuba, their equidistribution theorem. So sometimes it's called the simultaneous equidistribution theorem. So they proved in the simplest form, they proved that if we have a bunch of polynomials, each having at least one irrational coefficient, and we have intervals, subintervals of the unit interval, then we can prove the following equidistribution results. So in other words, this limit exists and it's equal to the product of these intervals. And Arkhipov, Zubarikov, and Karatsuba proved this theorem in the late of 1970s. And so in fact, they proved a much stronger result for multivariable polynomials in multidimensional setting. And they proved some quantitative forms of this theorem. So not only the existence of this limit, but they also showed how fast this quantity converges to this limit by using some sophisticated number theory, which, for instance, is based on this, what they call the multi-parameter Vinogradov mean value theorem. So they developed a big machinery for the exponential sums, which were based on some refinements of Vinogradov mean value theorem in the multi-parameter setting. So it's a very, very interesting story. But the other thing which is interesting to me, so there is a natural question in the spirit of Khinchin about almost everywhere convergence in the Arkhipov, Zubarikov, and Karatsuba equidistribution theorem. So, and this question, so this is the question about the simultaneous equidistribution theorem. And so it's conjectured that for all Lebesgue measurable sets, subsets of the unit interval, and for almost every x, we have the following convergence whenever the underlying polynomials each has at least one irrational coefficient. And so this problem is very closely related to norm convergence for the multiple, norm and pointwise convergence for multiple ergodic averaging operators. So let me tell you a few words about the norm convergence, because norm convergence, because it identifies what's the limiting behavior of the averaging operators of this form. So here we assume that we consider averages of this form, and so the norm convergence, for instance, on L2 along for the bilinear operators of this form along linear polynomials was established by Furstenberg in 1977 in the context of his investigations, in the context of his proof of Szemeredi theorem. So are there any questions? Yeah, sorry, because I didn't hear you.
Can you hear us?
Mariusz, can you go to previous slide?
Yes.
Now, in this, I'm missing something, maybe something stupid. You don't want the PIs to be independent in a heap of Chubarikov-Karatsuba?
I think that they don't have any independence.
But
All the same. Yeah.
Yeah, okay, but then this, yeah, okay, yeah, then okay, if you need some, if you want to have some non-trivial results, yeah, okay, you need, that's right. I think that I forgot this this assumption. Yeah.
But if you do assume independence, that it already, I think, contained in original paper of Weyl in 1916. Because by Weyl criterion, you make it. It has multidimensional section there. This is actually the paper you say you like. I think in Weyl's paper, it reads this under assumption of independence.
Yeah, but you know, but here, okay, but yeah, but here, okay, I mentioned the Arkhipov, Tsubarikov, and Karatsuba because you know, they also proved, you know, this quantitative bounds.
Estimates, which big deal for them.
Yeah.
But
Yeah, you are right. You are right. That's right. I think that you are right. That he has also this this multidimensional version of which is essentially of this form. But they, you know, this is what they. Yeah. I think that you are right.
So please go ahead.
Okay. Any other questions? Okay. So let me let me go further. And yeah, thank you, Vitaly, for pointing this out. I have to take a look more carefully, you know, for Weyl's paper. But I think that you are right. Now I have some vague recollection that this was considered by Weyl as well. Yeah. So and the bilinear problem for linear orbits was so the limiting behavior was established by Furstenberg. Then in the mid of 1980s, Bergelson started to consider these averaging operators systematically in the context of weakly mixing, in the context of weakly mixing systems. And then Furstenberg and Weiss considered this parabolic situation, bilinear parabolic situation, and also the trilinear situation for linear polynomials. And then we have groundbreaking papers of Hosen-Kra and Tammy Ziegler, where the general situation for linear polynomials was understood. And in 2005, Sasha-Leibman proved the norm convergence for the polynomials with integer coefficients. And so this is essentially how the situation for norm convergence look like. And in the 1990s, also Bourgain established pointwise convergence for the bilinear averaging operators along linear orbits. And so, and here now a central open problem in pointwise ergodic theory. This is the conjecture of Furstenberg-Bergelson-Leibman. So if we consider a nilpotent group of measure preserving transformations of a probability space and polynomials with integer coefficients, then we ask about the almost everywhere limit for this kind of averaging operators. And the norm convergence in L2 was established even in a nilpotent setting by Miguel Walsh in 2012. And so Bergelson and Leibman also showed that L2 convergence may fail if G is a solvable group. if we go beyond the class of nilpotent groups, so then this convergence may fail even in null. And so now let me tell you about this my result with Ben Krause and Terry Tao. So we were recently able to establish pointwise convergence in the bilinear setting for the averaging operators, the Furstenberg-Weiss averaging operators of this form. So one orbit is taken along n, the other is taken along polynomial with degree bigger or equal to, and we have for this almost everywhere convergence and non-convergence. And as a consequence of this, we can say something about this almost everywhere equidistribution theorem. So if we take any subsets of any Lebesgue measurable sets of the unit interval E and F, then the following limit exists. And this is a consequence of this theorem in particular. So, and let me tell you a few words about the proof of this, but let me start from the linear situation. So for Burgen's averaging operator, because I wanted to say something about the Weyl inequality in the multilinear or bilinear setting. And let me start from Weyl inequality and application of Weyl inequality in the linear setting. So this is how. So Weyl inequality played an important role in Burgen's proof, and so in particular, so now we have a inverse form of Weyl's inequality, which is very useful in this kind of problems. So, and it says that if our normalized exponential sum is bigger than delta for certain delta, which is not too small in terms of the underlying scale, then there is a Q, an integer not too large in terms of delta, such that these quantities have this, we have the inequality of this form. So in other words, it says that every coefficient of this polynomial is belongs to major arcs. In other words, they are approximated by rationals which have small denominators, and Q is a denominator, and the smallness is controlled in terms of this delta that we have here. And now, for instance, if we assume that our function, the Fourier transform of our function, is supported on minor arc, which is the complement of major arc, then so this inequality says precisely the inverse form. It says that, you know, this part should be very small, should be negligible, because our frequency cannot be supported simultaneously in major and minor arc. So this is essentially what we can get from deduced from Weyl's inequality, and especially this inverse form is very, very useful here. And so, and in the bilinear situation, so when we started to work on this problem, so it turned out that the classical Weyl inequality is inefficient, and that was one obstruction. The second obstruction was inability to apply Plancher's theorem. So we had to proceed differently, and so this is what was. And at that time, it was not even clear how to formulate what the Weyl inequality in the bilinear situation should be. And the most naive approach is to see what happens if we assume that F or G, what happens, if F or G is supported on minor arc. So in other words, if it vanishes on major arc, which is the collection, the union of intervals of this form, which are centered at rational fractions with small denominators in terms of the underlying scale. And it turned out that one can, so if we assume that we are in this situation, then the L1 norm, so we can beat the trivial bound that comes from Cauchy-Schwarz inequality, which gives the constant 1 here, and we can say a little bit more. We can gain some decay, logarithmic decay in terms of the underlying scale, and we have this. And so that's so this inequality, this is the core of our argument, and a lot of things can be derived in the proof from this. So it's based on the main tool. It's to prove this inequality is the inverse theorem of Peluse and Prendiville. And then we had to use some other tools like the Ionescu-Wenger multiplier theorem and Hahn-Banach separation theorem and LP improving estimates of Hahn, Kovac, Lacey, Madrid, and Young, which are derived from the Vinogradov mean value theorem. And so let me tell you a few words about the Peluse and Prendiville. So this is the inverse theorem, certain structural result, which says that if L1 norm of this multilinear form is large in terms of this delta, then we can find an integer not too big, and such that this average restricted to certain arithmetic progression with spacing Q is also large. And here it's important that we have this polynomial dependence on delta. And this result was used by Peluse to give a quantitative bounds in the Bergelson-Leibman theorem for polynomials with distinct degrees. So she was able to derive the following bound. And this was also the key in our in this what I on this previous slide called the bilinear Weyl inequality. And so now let me tell you about this, what we can prove about the so let me tell you what we can say about the pointwise convergence for these averaging operators whenever the underlying measure preserving maps commute and polynomials all have distinct degrees. So for instance, in the single transformation case, so we can establish in the bilinear situation the pointwise almost everywhere convergence for this whenever P1 and P2 are polynomials with distinct degrees. Or in the multilinear situation, we can establish pointwise convergence whenever for monomials, when orbits are taken along monomials. Then we also know that we have pointwise convergence here. And so here the two the key tool as before, this is this multilinear Weyl inequality. Here it can be proven for all polynomials with distinct degrees. By the way, this inequality can be also used to deduce the this bound in Peluse theorem by using some argument of Bourgain, which was developed in 1988, I think, in his Roth theorem, quadratic Roth theorem on the real line. And as a consequence of this pointwise convergence here, we can also deduce the following almost everywhere equidistribution theorem for these polynomials with distinct degrees as long as alpha is irrational number. So and also let me tell you what so we also made some progress on this problem when we have in the parabolic situation when we have two commuting transformations. So this averages correspond to the following configurations in Z2. And so at this moment we can prove the following analog of Weyl's inequality, which we believe that will be also important ingredient. And now the abstractions to prove to establish pointwise convergence lie more on the harmonic analysis side, not on the additive combinatorics side. And also as a consequence of this, if we are able to establish this pointwise convergence for this, as a consequence we will have this equidistribution theorem for two irrational numbers alpha and beta. So we'll be able to deduce something like this. And Finally, let me tell you that, so here we talk about this, the Weyl inequality on the set of integers, but in order to establish pointwise convergence, we need to understand the averaging operators, not only on the set of integers, but also in the situation of finite rings or p-adics. And that was the motivation to start to think about the following problem, quantifying Peluse or extending Peluse theorem with the quantitative bounds in the context of topological fields. So if K is a locally compact topological field with non-trivial absolute value and Haar measure, so here we can think that K is R or K is the complex field, or so for us, the main motivation was to understand the situation of p-adic numbers. And we have polynomials with distinct degrees, no constant terms. Then we can establish the following result. So this is the analog of the quantitative form of the analog of the polynomial Szemeredi theorem. And so this, what we have done here, before that it was, so initially it was considered by Bourgain in the 1998, I think, on the real line for these configurations. And then recently it was discussed by Durchik, Guo, and Ross, and Chen, Guo, and Li in the context of this. But they were, because they used heavily Fourier methods, classical Fourier methods, they were unable to go beyond the trilinear situation. So this is what we were able to do thanks to Peluse ideas. We were able to push things further and go beyond the arithmetic, beyond the situation of length 3. And so we can also handle in the context of this topological fields, we can also handle these configurations of this form, and also more general for the corners. And so let me also mention that the quantitative bounds for this kind of problem in the context of finite fields were studied by Boris Kuitsa. Here, let me also mention that, so we can also say something about the finite fields, but we have to assume that the characteristic of those fields is bigger than this number, the degree of the largest degree among our polynomials. Then we can also say something about we have analog of this theorem in the finite fields. But so the assumption on the finite characteristic is because we want to avoid the situation that we divide by 0 sometimes, and so we believe that this can be extended to the general situation, but we haven't tried. For us, it was the most important. It was this situation QP, because this is the model case for pointwise convergence to a certain extent, and so that was the motivation to understand the p-adic situation. And the other cases like the real line and the complex plane, it was just because we observed that, okay, if we put more general notation, then everything works. Okay, so that was my last slide. Thank you very much for your attention.
Are there any questions? I have a question. Can you say something more about what's the special motivation for studying QP?
Sorry, can you say, because I can't hear you. Can you?
Can you say something more about the special motivation when studying the p-adic field?
Yeah, because okay, so we you see that the p-adic situation. So when we start to play the game with the circle method, at some point when we are on major arc, there is a natural that, you know, the analog bilinear or multilinear analog of let me go back to this okay, to this average. So the so when we are on major arc and when we do some approximations, you know, then it turns out that the analog of this sum arise in the context of finite rings, and so we need to have some non-trivial estimates, and they are so this then this the finite ring setting can be thought as an analog of classical complete exponential sums, and so that's the reason. And sometimes, you know, some estimates, we realize that some estimates, if we lift the situation from finite rings to the corresponding p-adic situation, we have more tools to handle, to provide some estimates, for instance, for exponential sums, which are efficient in the context of the problems that arise here, and that was the reason.
Thank you. Are there more questions? If not, let's thank Mariusz.